lotus has long been a symbol of purity. Perhaps it's because its leaves always stay so clean and dry. Science describes them as superhydrophobic or highly water repellent. For the lotus, it means more sunlight and less bacteria. For us, inspiration.
Nature is much better than us in designing nanotechnology that works.
Take a close look at a lotus leaf and you'll discover a double layer of textures. Waxy microscopic bumps are covered in nanoscale hairs which trap a thin film of air. When rain falls, hardly any water comes into contact with the surface and droplets roll straight off, taking dirt particles with them. Chemists and engineers at Sydney University are looking at cheap and simple ways to imitate the Lotus Effect.
I'm immersing this silicon wafer in a solution of stearic acid many times, depositing each time a thin layer of crystals. The crystals are hydrophobic and also they're very rough.
The more crystals, the more air the surface can trap. Dipping 20 times gives Kiara the surface she's after.
So if I do this many times, I end up with something that looks like this, that has a very high contact angle.
A high contact angle means the surface is water repellent. On this surface, water can form a near perfect sphere and roll straight off. With a contact angle of 172 degrees, it's as water repellent as a lotus leaf. This piece of copper has a hydrophobic coating that's so water repellent that I can't wet or stain it, no matter how hard I try.
So if we had, say, clothing and paint and in general materials that are stain repellent, water repellent, we wouldn't need to wash our clothes so often and we wouldn't need to maintain all the surfaces around us so often. So the superhydrophobic idea is one that really appeals to people.
Biologists have also noticed how some animals living in arid deserts use their body surface to catch water from the air. Like these beetles from Africa's Namib Desert that harvest water from fog. Their mostly waxy exoskeletons are patterned with tiny wax-free patches that are hydrophilic or water-loving. Condensation can only occur here, so when the drops grow larger, they run along hydrophobic channels into the beetle's mouth. Could this same technique be used to quench our thirst in drought conditions?
So that's another very interesting example where nature really optimizes surface properties. And I've been working for a long time in thin film de-wetting, so that immediately struck me as a very easy way to produce hydrophilic bumps on a hydrophobic background.
The process is surprisingly simple. Two polymers are spin-coated onto a substrate to create a double layer. When heated, the top unstable polymer breaks apart, leaving a surface that looks like this. Watch what happens when humid air is passed over just a couple of square millimetres of this material. Over 5 minutes, water condenses on the hydrophilic top layer and grows into larger drops. How much does your surface improve condensation?
So a test piece like this, you might collect 40 to 50% more water than a corresponding flat film.
That's a really impressive increase. What would happen if you scaled it up to a prototype?
Yeah, if we turn this into a pattern that existed over 1 square metre, we might be able to collect 2 to 3 litres of water per square metre per hour.
Could be a bit of a drought buster.
Yeah, we hope so.
Large sheets of this surface producing a few litres from each square metre every hour could tap into a welcome new source of clean water.
People can see the promise of collecting water in a way that's sustainable, that won't require a big expenditure of money, and potentially can solve the problem of drought in Australia, for example.